name's Tom Mott. I'm president of the Memphremagog Water Association. I am going to read this because I've got so much to cover I can't remember a darn thing, so bear with me, okay? We're starting off with the annual board meeting and then followed by a symposium of layers of the land, which is all about this incredible geographic land we have going up Lake Memphremagog. We have a lot going on in NWA right now. Two longtime board members of NWA, Mary Pat Golding and Jennifer Hopkins, are resigning from the board. And Mary Pat has been vice president, then president, and now our secretary. She's up for nomination to be renewed and has declined. I acknowledge Mary Pat for her having her heart in this for so long and her guidance. But I would also like to acknowledge her husband, Chuck. Where's Chuck?
He's in the back.
Chuck, thank you. Who has been sharing Mary Pat with us for so long. I mean, that's really something. Stan Chop, who's a longtime board member, has accepted the nomination to be our secretary in the interim. And he has been our secretary before. He's been on our board for a long time, and I just really appreciate your help. Jennifer Hopkins, also another longtime board member, has submitted her resignation to NWA as bookkeeper and treasurer and will stay as long as December to ensure that we are able to continue what we're doing without any hiccups after she leaves. Not only has she been our bookkeeper and treasurer for years, she's also run our aquatic invasive species, AIS, for programs pertaining to grants, aquatic weed removal, breeder programs at Newport, Strawberry Acres, all over the place. And she has been our sanity check for grants and proposals. She will partially be replaced by a future executive director, Kendall Lambert, who has been with us for quite a while, or she's been with us and then she left for a while and she's back as our administrative specialist. Now I lost my place. So Cheryl, Kendall, is going to be working closely with our new CPA, Cheryl LeBoyne, who is local, and she will be handling the bookkeeping, and Michael Croto, who's on our board, will be our treasurer, and be working very closely with her. I would like to give special recognition to Mary Pat and Jennifer for having our back, their guidance, and doing their due diligence for making MWA what it is today, present them with some gifts of appreciation. And long may you drink and be happy.
Oh, thank you. Thank you very much. Thank you. Thank you.
So we've got quite a transition going on here. When it first came about, it was really devastating to me because it was all happening on my watch. But my view of life is a breakdown is nothing but an opportunity for a breakthrough. So I'm looking at how we can move forward and grow to the next step. With this said, to begin with, we are in the process of hiring an executive director. When we are in position for that, Kendall Lambert, who's our administrative specialist, has given us a positive sign that she would accept the nomination. But to get there, we need to get a better handle on our financials to ensure that we are fiscally responsible to move forward with that. As stated, we're hiring Cheryl LeBoyne, and we have moved to from QuickBooks Desktop to QuickBooks Online. And we're also looking at other systems that will integrate with QuickBooks Online, which will populate QuickBooks Online, and it'll make it easier for our staff to track and record any expenses. We're also going forward to putting a major focus on fundraising. We really have not been doing a lot of fundraising. Most of our money comes in from membership and from grants. We are mostly grant funded to the tune of around $1.5 million a year. And with the current administration, we don't know how solid that is for us. So we need to look elsewhere to cover our backs. So we are going to be putting together projects to fundraise from individuals, from corporations, to carry this to the next step. MWA, it all starts here. 75% of the lake is in Canada, 75% of the watershed is in Vermont. And so whatever we do here carries forth all the way up to Canada and beyond. So MCI is amazing what they do up there, but again, it starts here. So our group has done an incredible job in riparian and all these other things they're working on, but we need to go farther. So, your donations would be appreciated. With that said, I'd like to take a minute to acknowledge our team. Patrick Curley, who's our project coordinator, Gabby and Ben, he's our project manager. Gabby and Ben are our project coordinators, working on a number of different projects. Kendall, our administrative specialist, Marnie, who's our vice president, Mary Pat, our secretary, and Jennifer, our bookkeeper and treasurer, and our board members, Karen, Stan, Beth, Michael, and Farley. This couldn't be done without you all. We are a team. Moving forward, I would also propose that we expand our board. Our board is people right around Newport. I want to get more collaboration, more communication throughout the watershed. So we go as far east as Island Pond and as far south as Craftsbury, try to get people from every different town in the watershed or every lake association involved. And we can change the terms from 3 years to 1 year, or whatever, just so we can get more people, get better communication and collaboration. I think it'll make us all much stronger as a team. And before you get rid of me, almost, MWA has a scholarship program, and I would like to announce the recipients for 2025. Memphremagog Watershed Association is pleased to announce the recipients of the scholarship awards of 2025 graduates from area high schools. In keeping with its mission to protect the environment and the natural beauty of the Memphremagog Watershed, MWA scholarships are intended to assist students whose high school studies and activities have led them to pursue education, career paths in sciences and environmental studies. Funds for scholarships come from MWA memberships, contributions, and donations for the community. This year, the scholarship funding is shared by 4 highly qualified recipients. Luke Delariere of Derby, graduate of Stansted College. Is he here by chance? He's entering Rensselaer Polytechnical Institute. Josie Fortin of Newport Center and North Country Union High School, entering Middlebury College. And Natalie Neeland of Lowell and also North Country Union High School is entering Middlebury College as well. And Anya, I know you're here. Where are you, Anya? Hey! Anne-Marie Remmers of Montgomery Center and North Country Union High School is entering Wentworth Institute of Technology. In addition to congratulating these graduates and their families, the MWA wishes to acknowledge the many community members and organizations that are cited by applicants as sources of inspiration and guidance, from the important teachers to the family farms and neighbors, plus summer experiences through Governor's Institute of Vermont, Northwood Stewardship Center, Vermont Department of Fish and Wildlife, Missisquoi River Basin Association, Beta Technologies, Community College of Vermont, and North Country Union High School's Galapagos Field Study Program. For further information about the MWA, we've got it on our website for future applicants. And I believe without further ado,
But just so you know, I got a very nice note from Luke this afternoon.
Okay.
And he's headed to RPI like tomorrow. Wow. So he couldn't be here tonight, but he said how much he really appreciates our scholarship.
yep, we do as much as we can, and we just, our heart is in it for you guys who are taking advantage of it. Thank you. So, I think, where's Marnie?
Right.
Do we have anything more? Am I all set? We have a nominating committee?
You need to approve the minutes.
Oh,
Minutes in the treasurer's report.
okay. So, Secretary's report, we have approval of the minutes.
Now, there are members of MWA in the audience, and I believe you all got copies of the minutes. Does anybody need me to read the minutes from last year?
Absolutely not.
Thank you, Beth. There was something
So
astonishing that happened at the meeting, I can tell you that.
Do we have a motion to approve the minutes from last meeting?
So moved.
Do we have a second?
Second.
Any discussion? All in favor?
Aye.
Any opposed? So moved. Treasurer's report.
Okay. They got sent, I think, to the board late because I'm late on doing things because I do other things. So, and I'm not a trained bookkeeper. So this is an advantage that we're going to, I'm not sure about QuickBooks Online, but a bookkeeper for sure. But since I took over, we started with about $8,000. We were totally funded by membership. We now, thanks to Patrick mainly, Gabby, Kendall, Ben, who's recently come on, our balance sheet is, yes, I can't see either, just shy of $200,000 is what we have in the bank account. But this comes in, this goes out. We've got receivables right now of somewhere around $40,000. So we end up needing that, but we need the extra money. What we don't have is the money we can commit to a executive director. So yes, as Tom says, we need the money. You'll look at these sheets. We look like we're doing really, really good, and we are building up our war chest, but with what's happening with the federal grants, and we're funded by federal grants that come through the state and some state-only grants, some private grants. We've been very, very lucky, and how long this luck will last, we don't know. But what is important, I'll change my hat to aquatic invasive species, what is important is the lakes out there. We've helped 10 lakes with their breeder program over the years. It was started, Kendall started it, the state wanted us to do it. We've expanded over the years. We handle almost $200,000 of grants that come in and go right out to our fellow lake associations running a volunteer and paid breeder program. So that's my spiel. You can bring the money in. I'm here until December because it's going to take that long for people really to pull me out of what I'm tied into. So, and I'm still on the board if it's needed. So. Anyway, I do have copies of this if anybody wants to see. You know, we're doing well, but there are times when we almost don't have any cash. So that's my spiel.
Can I ask who seconded the secretary's report?
Karen.
Oh, Karen, all right, thank you.
So,
That's it.
any discussion on the treasurer's report? Do we have a motion to accept? As stated.
Nobody wants to.
Karen.
Do we have a second?
Second.
All in favor?
Aye.
Any opposed? So moved.
There will be an audit, guys, so you don't have to worry about it.
And there's copies here if anybody wants
Yeah.
to look at.
And we can mail them out also. We will be doing that.
So as I said, we're always looking for members so we can increase our strength as a board to get on our board. And we have a nominating committee, and we have a few people that are interested in getting on the board. Do we have someone here from the nominating committee?
Karen.
Karen? Thank you.
So Caitlin from Northwoods is interested. She submitted her information.
I think you need to stand up so they can hear you.
I know her somewhat. I worked with her over at Prouty with the students at the beginning of the summer. And I think that she would be a good candidate. Another person that I've spoken to, your neighbor Leanne, and she is interested. She needs more information, and I know that maybe you could help her with that a little bit. And that's what I have for right now.
Okay. So I think at this point, maybe we invite them to a board meeting and talk with them.
I invited her tonight, but she's got grandkids.
And Patrick,
Yeah,
you had some people that might be interested as well?
yeah, so I have 3 people that am courting.
Good.
I
Okay.
will keep names quiet for now. I don't
Okay,
wanna get
great.
against myself.
Is there any other business we need to discuss?
One last thing, NWA wrote a letter about the new waste boat regulations opposing the elimination of homeland rule and the decontamination standards. And it was suggested that we CC our local legislators on the letter because the legislators have been notified about it. So we need approval of the board to CC the local legislators.
So, what do we need to do about that?
I make a motion that we approve that.
Yep.
I'll second that.
Okay, all in favor? Aye. Any opposed? Great.
I didn't hear what she said.
We are making headway. It's a good thing we didn't
Well, there's
start.
plenty of time to eat.
That's right. Next up, I would like to introduce Layers of the Land. We could take a brief break for 10 minutes and grab some snacks and hors d'oeuvres while we're there. And then Jonathan Kim. Jonathan, he's a geologist with the Vermont Geological Survey, a division of the Vermont Department of Environmental Conservation. Will speak about the current geological work that VGS does with the academic partners of Watershed statewide. That's going to be fun. Okay. Stephen Wright, nice to meet you. Senior lecturer of UVM Geology Department will present on the results of the recent superficial and glacial geological survey completed in the watershed, and there'll be time for questions and answers after.
Tom, one thing, I
Yes.
would remind people to sign in if they didn't sign in.
Oh,
And they
okay.
can flip over the
If
sheet
anybody
if it's
came
not
here
right.
and hasn't signed in, it would be great to have your names. Otherwise, enjoy some apps, and we will resume in about 8 minutes for our discussions.
Appreciative we are, myself, Gabby, Ben, for how much work Jennifer does for MWA, soils, and goes to trials and tribulations with me when it comes to balancing, accounting, budgeting, planning, invoicing, getting to paying people. So it's a thankless job she's signing over there, but just everybody should be grateful that there's someone behind the structure of MWA that keeps things rolling. Mary Pat this now about her. When I showed up, it was COVID. I was like a lost puppy in the rain. I wanted to live in the Northeast Kingdom, and I didn't want to work remotely for my job anymore. And I just pestered the hell out of Mary Pat, and I said, "Let me do some work for you. I want to do some work for this organization." And she took a chance, and I'm still here. And she's finally being able to be relieved of all the duties that go with MWA. We're just extremely grateful for her work as well. So thank you, Mary Pat. And now I want to have all of your attention focused on John Kim, who's going to teach us about rocks.
Okay, so a while ago, Kendall and Patrick contacted the Vermont Geological Survey about possibly doing a talk for your meeting. And so we started to discuss, so what would be reasonable for this audience and what would they like? So we started talking about, well, my thing is bedrock geology, and I do a lot of hydrogeology, hydrology. But then we actually have, the talk went to, so we should have 2 speakers so we can cover everything. And so I thought, all right, well, Stephen Wright from University of Vermont, who has mapped the glacial geology around here in extraordinary detail, that it would be great to invite him and have him for part 2. So my mission is to give you, there was a request that I talk about, well, what type of watershed studies do we do at the Vermont Geological Survey? And what do we do? So the first part of my talk is going to be walking through one of our studies at a nearby place, not an hour drive. But anyway, then I'm going to go into the bedrock geology of the Memphremagog watershed, and then I'll go into a bunch of the work that I've done on and off in the past 2 summers, and I'll explain why it was on and off. So I've just, in Layers of the Land, I'm doing the exploring bedrock and hydrogeology. And so I just told you what I was going to do, but first thing is a holistic watershed approach. So when I explain this watershed approach, you're going to go, well, you just do that for this problem. No, what we do at the Vermont Geological Survey is we do every type of geology we can to try and deal with a problem. So it doesn't matter, I'm going to give you an example from cyanobacteria, but we would do the same thing for nitrate contaminations at farms, PFAS contamination at airports or in other places, or any of the type studies that we get asked to do. And I call our clients the folks at the Department of Environmental Conservation, Vermont Agency of Transportation, et cetera, that ask for our services. So I got this from your website. I quoted you properly, but what is a watershed? A watershed is an area of land that channels all precipitation from hills and mountains, forests and fields, draining it down to streams, rivers, and lakes. Nice definition. I love it. But one of the things as geologists we have to think about is that the general definition here is it's really heavily centric on surface water. And what I want to point out, and what we're always thinking about, whether it's contamination or whatever, is groundwater and surface water are a system. You can have a stream gaining water from groundwater, or you can have a stream losing surface water to groundwater and go back and forth. It can happen all year round, and it can be going in different directions. So I want to point this out. I wanted to say, okay, watersheds, great, but how do we work with watersheds and also consider this? So I'm going to show you one example, kind of soup to nuts of what we did for one of our major projects. Started in 2019 and ran through well, it's running right now, but I'll just kind of give you a summary. In Franklin, Vermont, this is the Lake Carmi watershed. I don't know if you've heard of this before. This is a small lake. There's been serious cyanobacteria blooms there for decades. And this is my colleague Ed Romanowitz from SUNY Plattsburgh, one of our academic partners, standing at the beach of a closed area for swimming. So let's just think about, so what we want to do is we want to understand the watershed, right? So look at here in orange in this kind of really A-frame shaped watershed is the Memphremagog watershed. You say, well, why don't you just study the lake? But you can't. You have to put all the layers together. I'm going to show you all the layers. I won't talk about these layers in great detail, other than that we do this for all of our projects. So the first thing we think about, what's the basement on this Lake Carmi issue? Well, the basement is the bedrock geology. So we went on, we made a bedrock geological map of the bedrock around Lake Carmi, put it together here, and then I drew cross sections. If you cut through the earth using a figurative knife, and then you draw based on the structures you see on the surface, what it looks like at depth, this is what it looks like. Over here near the Franklin Country Stores is a major ancient thrust flow right here, and then that produces lots of water. That's something to think about. Ignore this, the structural geology. Well, what we're doing, as I'm telling you, we're going to do the bedrock mapping. We'll do the structural geology, try to understand the basement on all of our projects. The next step up, and this is Stephen Wright's map from Lake Carmi. We hired him to do a superficial or glacial geologic map of Lake Carmi, but I just want to point out some highlights here and why this is important. From Stephen's mapping here showing there's the watershed boundary in orange, right? And all the different colors are all the different types of superficial deposits that Stephen mapped. And what I wanted to point out to you in particular is look at these deposits in blue at the north end, and then in green at the south end. And what Stephen, just like the bedrock geologists do, is he makes cross sections across various transects on the lake, cutting down to the bedrock. And so what do things look like at depth? And look what you see here on A prime, which is this cross section right along the lake outflow, is you see, look, the superficial parts of this are quite thick. They get to over 60 feet thick. And what Stephen has mapped is in blue. These are actually Champlain Sea marine deposits that are interlayered with, we'll just call the Pleistocene right here. Diamond. Well, anyway, it's basically till, but these are actually freshwater Lake Vermont type deposits that are interlayered. And so here we have at the north end of the lake, we have really, really thick deposits. So could that affect things? And it's sitting on top of the bedrock. So then, what's our next step? We're going to look at all the wells we can in the area and look in 3 dimensions. Okay. So from our Vermont state database, we can look at all the wells that have accurate locations and look in 3 dimensions at what we see. So here is around Lake Carmi, here is the watershed boundary in orange. And so all the gravel wells are shown in this light green, and all the bedrock wells are shown in the lighter pink. And then around here are the dark purple, darker purple are the bedrock outcrops that we've seen. So we put this all together, and we can come up with a map with 3 different type maps. But one, if you look over on the right map, depth of bedrock map, called an isopac map. Look at where the superficial deposits that Stephen Wright map are thickest, up to 60 feet thick over here. There are some that are thicker to the south, but look along the sides of the lake to the east and west. You see these lines, and there's LiDAR shaded relief under there, where the darker shades are steeper slopes and the lighter colors are gentler slopes. But anyway, there's hardly any superficial deposits on the sides of the lake. And so they're all right here and some here. And that's just from a first pass with the wells. Now let's do some other maps. So we can take that same information, right, from the wells, what Stephen done, where we have bedrock outcrops, etc. We'll make a map of what the bedrock surface looks like underneath everything. Imagine we're pulling the roots, rocks, grass, trees off figuratively in our computers, and we come up with this. So look what we have here. The warmer colors, pink being the warmest, are areas where the bedrock is highest, right? The colder colors are where the bedrock is the lowest in elevation, right? But look what we have here. So when we look at what Stephen came up with on the superficial map and the wells, that it's the northern part of the lake has that deeper, those deeper superficial deposits. Wow, look what's going on here. To the north end of the lake, everything is really low. And if we figuratively pull everything away, this looks to be probably a pre-glacial bedrock channel, right here, right? Something that was filled in that we don't see unless we do a lot of our analysis. Now look to the south, another one. So then I said, well, look at the bedrock of the basement, look at the superficial deposits, look at the wells, do 3 different types of maps just to start thinking about what the plumbing might be to the lake of groundwater and surface water. And so I'm just going to move to this, and this is kind of a neat depiction of what's going on. So this is how we're thinking. We want to think, all right, we've got the air flow over the watershed, okay? Here's the bedrock geology. Here's the superficial geology. Putting them on top of each other and thinking about it. Then, let's put the other maps I was talking about together, which are the bedrock surface elevation map. And then here is the isobac, the thickness of essentially the soils right here. This is actually a static water level map, but I'm not going to talk about this much. But anyway, so you see we've put all this data together for just even starting to think about the next stage, which is, let's sample the water, the bedrock aquifer groundwater, the shallow superficial groundwater, and the lake water and the tributaries. So here we designed this project, so all the bedrock wells we sample are purple dots. All the very shallow wells, that what we would call dug wells, where there's a well tile, are the yellow stars. Tributary samples are shown in green triangles, and lake samples are shown in light blue diamonds. So we sampled a lot, right? So we built the bedrock basement, the superficial geology, the wells, and now we're starting to look at the chemistry. In addition to doing the chemistry of the sites I just showed you previously, we also, using a geoprobe, which is basically a fancy drill rig, we actually put in 9 monitoring wells to a depth of 20 feet around the lake to look at the groundwater in the shallow aquifer, right? So that's all these locations in the brown bullseyes, okay? This is us looking at the cores. Stephen was one, that's him right there. But I'm describing these cores in detail. I won't go into the deposits in any detail other than to show you that we have the exact composition of the various superficial or soil layers described. And so this is kind of a summary of, like I said, there's a lot of chemistry in here, and I'm just going to allude to it, but if you look, this is a box and whisker plot. But basically what we're saying, so if we look at the bedrock wells and essentially put together what average levels of phosphorus, which is the active metal in feeding cyanobacteria blooms, so we sample bedrock wells, springs, tributaries, the lake, but these new monitoring wells that we saw, we find that they're actually right at the same, near the same level as the tributaries, at least the lower half of the 2 quartiles here, so that we've got phosphorus, low amounts from the bedrock wells, the shallow, very superficial wells, 20 parts per billion average. The tributaries have about close to 100 parts per billion average. The lake has about, say, 50, but the monitoring wells are in this range. So we built this whole story, and now we're getting chemistry. The next step, and this is meant to be a blur for all of you, because it wasn't just phosphorus we did. We did 34 other parameters. So our story is very complicated, but we've looked at everything we can. So just as an example, this is phosphorus, nitrate, chloride, sodium, hardness, and strontium, barium, silica. I mean, things you don't want to remember from your chemistry class. But anyway, so we have all this information by location, by well type, by tributary type, or monitoring well, for all going all around the lake. So what happens here? We end up, for every one of our projects, no matter what it is, putting together a 3-dimensional conceptual model. And a three-dimensional conceptual model here is this is going on the east side here. So see here, that's the west. I've got them turned around because I'm looking from the other direction. But so here's the Lake Carmi Basin with sediments on the bottom. Here's the CZFP, the Fairfield Pond Bedrock Formation. PT is the Pleistocene Tills that Stephen mapped. And then we look at every type of well that we have. Here's the bedrock wells, averaging 10 parts per billion. The shallow wells, averaging 20 parts per billion. We have tributary surface runoff at 90 parts per billion. And then from the monitoring wells, we're now, I actually have to edit this a little bit to say that we can actually have up to 75, 80 parts per billion coming in from the shallow monitoring wells here. So do you see it? This is our story, right? I'd be glad to talk about this for hours if you want, but this is what we do for all of our projects if we have the funding. So now what I'm going to do is I'm going to go into, like I talked about, bedrock geology of the area and of the watershed, and then finish with some progress. So this is also from your website, just showing, so Patrick sent me the GIS polygon from here showing the watershed in the United States. I know it goes up into Canada. I didn't put this on the maps, but just to show you know that I can show you exactly how the bedrock geology connects. All right, so there's the polygon I received from Patrick, just showing you all know where your watershed is. Don't have to go in any detail there, but let's go to the next one. Let's introduce the bedrock geology of Vermont, okay? In Vermont, the bedrock geology can be divided into belts, north-south belts, where the rocks of the same composition and age can be grouped together. It happens to be that virtually all of the contacts between these different north-south belts are faults, major faults, okay? So over here, this is the Champlain Thrust, if you've ever been to Burlington, right around Lone Rock Point. That's actually right in here. This is the Heinsberg Thrust, right in here. This I put on what's called the Dog River Fault Zone is actually right here, okay? And that's a major ancient fault also. And when I point out, this is my good colleague Alain Tremblay, who recently retired from the University of Quebec at Montreal. That fault in Sherbrooke is called the La Guadalupe Fault. The same faults go for miles and miles, or kilometers and kilometers. Everybody thinks of them that they end at international borders or state that they don't. They keep going, and we need to think about, and I think when you think about your lake, and everybody keeps pointing out, the geology doesn't end at the Vermont border. It continues, and in some cases becomes more complex in southern Quebec. But anyway, just going through here, so we're going to be talking about mainly this is the Newport quadrangle, the 50 square mile area that I'm mapping. And your watershed is in here, right here between here and here. So you're mainly in what's called the Connecticut Valley Belt, a fault contact with what we call the Roe-Hawley Belt. And just so you know, when you think about the rocks that compose most of your watershed, they go into southern Quebec, where they're called the Gaspé Belt, and they go all the way up to the Gaspé Peninsula, okay? If we follow this down to southern Vermont, they go through Massachusetts, through Connecticut to Long Island Sound. Okay, so it's not like they really end at state borders. So let's just go through the geology, bedrock geology, so you have some idea, okay? I'm not trying to take you deep in. Like I said, that would take, if you want to keep buying me beer afterwards, we can keep talking. But let's just talk about the watershed in Vermont, on the Newport side. Okay, right here, coming down the west side of Lake and out the southwest side, is a major ancient fault that actually puts rocks that are 460 million or older on the west side against these rocks, which are probably 390 to 400 million year old rocks on this side. So think pale blue, young, and then we're looking at these tans and some of these lighter reds. Those are much older. And there's a strong fault right here that actually juxtaposes, that actually pushes these rocks, the younger ones, over the older ones. Okay? The other thing.
Could you step that way a little bit so you can see?
Yeah, okay, sorry.
That could be helpful, thank you.
All right, so then the other thing to think about, so these are mainly what we call metamorphosed sedimentary rocks from one ocean basin. These in pale purple here are from a younger ocean basin that then was pushed together along these ancient faults with these older rocks. These rocks were assembled by a mound building event about, say, 450 to 460 million years ago. This later event, these younger rocks were deposited about 400 million years ago and then were deformed and metamorphosed and thrust around 380 or 390 million years ago. So this isn't the Atlantic. It's not the Atlantic 1 before. It's not the Atlantic 2 before. This is the Atlantic 3 before. This is the Atlantic 2 before. Because you think about plate tectonics, we're talking about different oceans that open, collapse during mound building events, open, collapse, open. And what we've done is we essentially keep adding terrains or rock slices to what we have here as we add them to the east. Okay, so this is, I deliberately stopped here, and I can go to the map in greater detail later. Now, I wanted to do this, and this is one of the only maps that exists for the whole Appalachians right now. They're working on another one, but I want to point out here, so I put Vermont on this map, okay? You are right here, okay? So, remember I said this is the Connecticut Valley Gaspé Trough. We call it the Connecticut Valley Belt in Vermont. So these are the rocks that are compose about 80% of your watershed, right? The fault between these rocks and this, the older rocks, which are also sedimentary rocks from the earlier ocean basin, essentially shown in green, right here, are basically faulted against these rocks about, say, 390 million years ago. But look at the extent of these things. Remember I was talking that that line, that fault, goes down here, through Vermont, through Massachusetts, and through Connecticut, okay? Then let's look the other way. And things get really exciting on the southern Quebec side, I guarantee you. You know about Owl's Head, you know, you can ski there, hike there, whatever. You know about Asbestos, Quebec. You know about Thetford Mines, Quebec. And so that's what we're looking at as we go up here. Okay, and what those are ophiolites. They're almost intact slices of oceanic crust from an island complex that were then, during the mountain building events, say around 460 million years ago, thrust up on land. Okay, so the mantle of the Earth is sitting on the current ground surface at Owl's Head and then going north. And this fault right here that goes to the north, like I said, it doesn't stop on the border. It disappears under the lake and then reappears up around the latitude of Magog and then up to Sherbrooke. This is just showing, so there, I won't go into this in any detail, but this is a pretty new 2015 map that Alain Tremblay and his PhD student Morgan Perrault made of southern Quebec. So here you are, here's the northern part of Lake Memphremagog, right here. Remember I was saying that fault goes up, up, up. Now look what happens here. So here you're up at Sherbrooke. You see all the bright colors? Those are volcanic rocks about 460 million years ago. Now those are on the same fault that's here, but those rocks were actually, those big slices were actually destroyed by the faulting millions of years ago. And one of the things to think about now, and now you're going, oh my gosh, he's nuts, is that the current ground surface is probably what used to be about 6 miles below the surface, right? So this is how I think. And so you're thinking about current ground surface, these rocks, and that the island complex, the volcanics, if I just looked at the exit sign, it said Sherbrooke is then, okay, it was Sherbrooke 33, Newport was 11. So anyway, so it's just 30 miles to Sherbrooke along the same fault that's there called the La Guadalupe. And I just wanted to point out, here's from Sherbrooke, here's these beautiful, beautiful falls in the Ascot complex, which is part of this island complex volcanics. And this is on one of the major highways in Sherbrooke. So all I got to do is drive 30 miles, essentially from here, and I'm on these rocks against your fault versus down here, we're looking at kind of just, less photogenic shaly rocks. So here I'm going to go into a little bit just about, so in 2023 and 2024, I have funding from the Vermont Survey and the U.S. Geological Survey to make a bedrock geologic map of the Newport Quadrangle. So what ended up happening was major landslides in 2023, and when I could have been up here more. I was actually helping map landslides and determining the safety of landslides all over the state under Ben's supervision. So that was the delay. And so then I wanted just to go into, why did we do map up here, right? Saying, well, you can map anywhere in the state. Well, I'm just going to talk about the environmental issue. All of our mapping is based on some environmental concern or issue that's brought to our attention. So we know that the Newport city wells have poor yields. Want to think about that. On the west side, in the Cram Hill Formation, there are some occurrences of arsenic in groundwater. In the lake, there's thoughts about, of course, phosphorus and cyanobacteria blooms. And then your CEO was telling me about his well that has elevated uranium, and that's in these Silurian volcanic rocks up here. And then there's some concern and talk about PFAS that may be associated with the landfill. So we're trying to generate information that could be used by everybody. So one of the reasons that we went after Newport is most places in Vermont have been mapped since the advent of plate tectonics, okay? So recognize that the Earth is composed of rigid plates that collide with each other, make mountain belts, get eroded, make oceans, right? And that took a long time to figure out. Well, your Newport Quadrangle was last mapped in 1951 before anyone knew anything about, really about faulting and about plate tectonics. So this is the 1951 the publication on our website. So this is essentially, I'm not going to go into this in any detail, but just showing, so far I've been around up at Eagle Point, down various places looking at, here's the Newport exit, looking at the intrusive contract between the granite, which is probably about 365 million years ago, and the Kyle Mountain Formation, which is slightly younger than the Waits River Formation, which is most of your watershed. And then in the granites, one of the things you'll notice once you get off at the first Newport exit, you'll see, well, the granite's solid, but then why are these subhorizontal sheets? Those are called sheeting fractures. So as the earth unloads itself by erosion, you end up getting subhorizontal planes. And so, and the subhorizontal planes get more closely spaced the closer you get to the surface. So we map those because that's something to think about with groundwater. Okay, I'm going to go into these later. in the next couple slides. But anyway, looking at the bedrock geology in great detail in terms of the structures, the folds, the faults, what we call cleavages, the beds, because those are all can be conduits for groundwater, okay? And remember, because groundwater and surface water are a system, we just better know that stuff. So this is actually kind of humbling to me. So some of the big, huge ledges that you see along Route 91. So I have to tell the story about my wife. My wife grew up in St. Johnsbury. She graduated from high school the same year as me. So when they were working on Interstate 91, she and her friends used to ride their bikes on the interstate. When they actually had, I mean, so think about that. But now there's on I-91 that was completed in, I think, the 80s. And so I feel like I'm the first one that's been on the interstates to describe these rocks in detail. And so let me just show you how I think. So this is the Waits River Formation right here. So this is basically was once shales and limestones. But this is what we can unravel from the structures right here. So what I've learned, it says S0, S1 composite. Just think about that's the first thing. And then pink is the second thing, and yellow is the third thing. So here are the earliest structures doing this. You see them folded around like this. But then you have these white lines are folded around by a full generation that you can see it arcing things like this, like this, like this. But it makes a cleavage that's the pink, right? And then if we look away from the original beds and then the cleavage in pink, the fractures in yellow. So we map those, we measure those. And so this is all putting together, and somebody which came up to me talking about, in 3 dimensions, we want to know what's under the ground for putting these data together and sharing it with everybody who wants it, you know? And so that's what I'm in the process of doing. The granites themselves are really interesting. This is Peter Strand. Here's right near the Newport exit, him pointing to one of these big granite outcrops. But look at this, these cracks in the granite. Granites are notorious for having lots of cracks. In fact, that's how they end up making them easy to quarry. And once again, ignore this. But one of the structural information. But what I want to point out here is, so up near the border with southern Quebec, the granites develop 3 sets of cracks. One that's subhorizontal, one like this, and another one like this. And you make perfect geometric blocks. And not only is it cool, but that's what we want to think about with groundwater plumbing near the surface. I call them Lego blocks. And the last thing, just to wrap up, we haven't got started on this, but we can actually do quite a bit with combining the bedrock geologic map I'm doing with this geophysical logging, where we lower lots of fancy tools down individual wells and get an enormous amount of information in 3 dimensions about the wells that we can put together with the bedrock geologic mapping I do. That's a borehole camera. That's a temperature meter. That's natural gamma, which is natural radioactivity. That's a caliper. That's the borehole diameter. And this is a 3D radar image of the hole. And that's a heat pulse meter that measures the direction and velocity that water is moving into the well. And we can use this to put together these logs, which I'm glad to be talking to you because I'm actually about to give myself a hook in 1 minute. Well, we can put together snapshots from the borehole camera with the different logs to look at wells. You know, we've looked at wells 1,300 feet deep, but the highlight of this one is a major fault here, and when you drill through the major fault, you got to a formation with cracks that produce lots of water. And we can use this information with making geologic maps where the different colors are the different rock formations. This is a fault where these rocks in yellow have been pushed over these. This was on the Lake Carmine map. And then we can do in 3 dimensions, putting this together with this, and this is what things look like in 3 dimensions. So that's my story, and that's what I went over. But I wanted to, because they asked, so what do you guys do if you want to study an area? So I went through that in pretty good detail for Lake Carmi, which we're still working on. And I showed you about the bedrock geology of the Memphremagog watershed and Newport in general, which I'd be glad to add more detail to. And then we want to be able to do some geophysical logging in this area if I can get permission to log some wells. And I'm also looking for permission to log bedrock geology on open tracts of land, getting permission. But I'm going to wrap up there and then introduce Stephen Wright from the University of Vermont.
Thank you. All right, well, you've had an introduction to the bedrock geology. My name again is Stephen Wright. I'm actually retired now from the University of Vermont. There's a story there, but anyway, what I'd like to do today is to give you an introduction to the materials that the glacier deposited on top of the rocks here. So this is the drainage basin that John alluded to and that you guys are focused on here. And this is an area that I've been mapping in now. This is my 3rd summer up here. I'm going to show you another map now, which is that same area, but divided into quadrangles. And this is how we decide where we're going to map. Essentially, we kind of pick these different quadrangles. And so over these last 3 years, I've mapped here, right where we are right now, the Newport, and then the Newport center quadrangle off to the west of us. Last summer, we were mapping down the Sutton quadrangle, which included the southern half of Willoughby. And during this summer here, I've been working up in the Westmore quad. So the point being that these are the areas I know fairly well. The other surrounding areas I know more peripherally, and so if you have questions, after the talk, and are living in one of these areas I haven't worked in, I can probably give you a general answer. Some of the areas that I have worked in, I can maybe be a little more specific. So I also want to mention that a lot of the work I've done is each summer I've brought in UVM students. The group on the left here was up with me last summer. We were at the Will of the Woods campground. Cheery looking group in the morning, eh? And these are 2 of the interns I worked with this last June. In general, what I'm going to do here is to give you a little time frame for the geology that we're talking about. Tell you a little bit about how the big glacier that used to be here moved across the area. Say something about this glacial lake history, the predecessor of the lake that's behind us here, and then talk about these different kinds of sediments that were deposited as the glacier was both flowing and then retreating across the area. And I wanted to introduce the guy in the group, the blue jacket, who's sitting right here, which is Ben DeYoung, who's our state geologist. And this work that I have done has been through the Vermont Geological Survey, which Ben is the head of. So he's another person that can direct questions here. So first of all, time frame here. This is a map that was put together by geologist Jack Ridge, who teaches down at Tufts University. And the important thing here, well, first of all, the lines that are drawn on here are showing essentially positions of the edge, the southern edge of the ice sheet, as it was retreating northwards across Vermont, or excuse me, across New England. So just in round numbers here, Down here across Long Island, Cape Cod, or those expensive islands down there, think 25,000 years. That's when the ice sheet was down there. By the time you're up at the border between northern Massachusetts, Vermont, New Hampshire, 15,000 years ago. So it's taken 10,000 years for the ice to retreat across southern New England. Up here, where we are, so this area right up across in here, between 14,000 years ago and 13,000 years ago. So the ice sheet started retreating very, very, very quickly when it got up into Vermont and New Hampshire. And so in round numbers then, think that this history of the Memphremagog Basin began about 13,000, or the ice sheet was retreating across the southern part of it about 13,800 years ago, and became a Quebec problem, probably somewhere around 13.3, 13.2, something like that. So just a few hundreds of years. And again, hearkening back to what John said, the rocks here are hundreds of millions of years old. So this glacial geology happened yesterday. We can count to 13,000. Most of us wouldn't want to count to 370 million. All right, so here's some of the rocks, or a picture of one of the rocks that John was talking about. These are the rocks. This is actually just a little ways north of us here. What it shows is a rock that has some scratch marks on it. It's been smoothed and scratched as the glacier moved over it. And these are glacial striations, and they're aligned parallel to my pencil here, and the compass shows that these scratch marks are almost north-south. So one of the things that we know, just by looking at this one example here and others in the area, is that the ice sheet was moving, pretty much from north to south when it was here. But let's step back a little bit, and this is a compilation of striations that I put together that are both my own measurements and those of geologists who've worked in this area during the 50s and the 60s. And we can see that, particularly when you look along the mountains here, the ice sheet was generally kind of flowing from northwest to southeast, some places even more due east. And then when you get down in the valleys, generally the ice was moving parallel to these valleys, more in a north-south direction. And again, that last measurement, that arrow right there is from that rock that I showed you just in that previous slide. So the other thing that might be obvious in this compilation here is that there aren't very many measurements in here. And this is because these rocks that lie to the east of the lake here are relatively soft. They dissolve easily in water. And so the scratch marks, the polish that the glacier produced when it flowed over it, has pretty much disintegrated away. You have to get very, very lucky to find the striations. So there's another kind of observation we can make though. So here we are down at Brownington Pond, just on the east side of I-91, a little way south of us here. And in this particular map, the red dots are actually bedrock outcrops. Places where you can actually see rock at the surface. And, no striations, no polish on them at all. And there's a new kind of imagery that was released just last summer. And again, this old imagery was pretty fantastic, actually, for most of us. This was, 10, 15 years old. But the new imagery looks like this. That's the same picture. So like that, it just has a sort of smooth look to it. But with this imagery here, you can see that there are these striations that look like they're running across the landscape. But again, we're not looking at an individual rock. We're looking at, a much larger scale grooves in the ground surface here. And they're oriented in that northwest to southeast direction. And what they are areas where the ice sheet has literally kind of left these little scratch marks except they're fairly big. And what they're scratching is this material that was deposited between the ice and the underlying bedrock, and the material that's referred to as glacial till. So, yeah, this is this glacial till I wanted to say a word about here because it is the ubiquitous glacially deposited material, almost anywhere in New England. In fact, almost anywhere where glaciers have existed. And I'm sure most of you are familiar with it. Most of the time we see this as, it's what makes all of our rocky soils. In this nice exposure here, this is unweathered, and the stuff is just like cement. In fact, it has this term, hard pan, but a whole mixture of rocks and various sizes here. It's really, really tough. And I tend to think of it as the crunchy peanut butter. This glacial till caught between the bedrock and the moving glacial ice. And essentially it consists of pieces of bedrock that have been broken off and ground up as it's moving along. So again, if you had really strong bread and and the peanut butter was relatively runny, you could essentially have a good analog for glacial till. But anyway, so this is the stuff that, again, surface water, rainwater, snow melt, has to generally get through this stuff to get down to the bedrock in most places. All right. So the next piece I wanted to say a little bit about is the glacial lake history, because that's, to my mind, one of the most interesting parts of this area here. And the general story with glacial lakes in most places, but in particular here in New England, is that they form when the glacier recedes past the drainage divide. So in this little model here, there's the glacier, it's flowing across this drainage divide, and as the glacier melts, the meltwater just drains away on the other side. The glacier retreats a little bit, crosses the divide, and now this meltwater gets caught between the glacier on one side and the drainage divide, and of course cools up to form a lake. So the glacier is still flowing this way. It's just melting faster than it's flowing forwards. There's water flowing off the glacier, within the glacier, into this lake. So it's feeding water into the lake, and it's feeding an awful lot of sediment into these lakes as well. And I'll say a little bit more about that later. So that's, it's a fairly simple concept, and geologists have known about this for a very, very long time. And the last thing I'll mention here is that elevation of that lake, of course, is governed by the elevation of the drainage divide. So here we are back at our basin, and one of the things we know, of course, is that a lot of those bigger basins off to the west of us here, water drains west into Lake Champlain. The Sunset and the Connecticut River, of course, is draining south down to Long Island Sound. And here, in the words of Howard Frank Mosier, of course, this is where the rivers flow north. And of course, we had our glacier, retreating to the north here once it had thinned and was flowing parallel to the river systems here, to the valleys. All right, so here's a model here, or a map rather, of the upper part of the watershed. Excuse me. And so here's the ice sheet here. So here's the Route 14 Valley, the Black River Valley, and there's the outlet right there, which is where Lake Elligo is. So that's where water's flowing out of the lake. There's the glacier acting as a dam. Up here, the upper Mississippi River Valley, same thing happening here. Only here the drainage divide is quite a bit higher. This is Belvedere right here. And so we have this lake penned up in here. This would be the Route 16 Valley coming down through here, and again drainage divide up in there, and another one over here. This would be Crystal Lake, and again water draining out of here. These two lakes have merged together now. Here's the Lake Willoughby drainage. So all of these different lakes are existing at the same time. at different elevations as the ice is retreating, because of course the drainage divides are at different elevations. So one thing that happened then is that, of course, as the ice sheet kind of retreated to the north, it started to uncover outlets which allowed these lakes to merge. And I want to show you several examples of those. First, right here in this area I was working this last summer. Well, actually, both these areas I've been working this last summer or the summer before, up on either side of Lake Willoughby. So here's an area, Lake Willoughby, and Bud Ebbett, a geologist who used to teach at Lyndon State College, what was still called that, actually mapped a lot of these funny-looking valleys up in here. So a lot of these guys here are going sort of in this odd direction, meaning they're going kind of across the slope of the valley. They're not going straight down the sides. And the same thing is true on a smaller scale up in here. You have all of these little drainage channels. And these are all abandoned channels. In other words, they're channels that have been eroded by streams, and the streams are no longer there. So this is an example of one of them, visible from the road here. You can see it there. There is a little brook coming down it, but the brook is teeny. It's not big enough to fill that valley by any means. So here I've actually put arrows in to kind of highlight some of these valleys here. And what I want to do is we're going to focus on the ones on the left-hand side to kind of show you a model for how I think these things form. So here's Wheeler Mountain, of course, here. And here's the ice sheet in the Willoughby Valley. And at this point, you have the lake, or the ice has retreated enough so there's a small lake in here. You could call it a pond if you want. And it's draining over this little divide, where the dirt road goes along that south side of Wheeler. So let's let the ice sheet retreat a little bit more. Now there's a channel down over here. You can see it right in here. And so this lake is draining out of here now and either back into the ice sheet or along the margin of the ice sheet. And we have a lake penned up at this elevation. Ice sheet retreats a little bit more, and this lake now kind of starts to sneak out around this part of the valley here. And there's another channel that's up. Whoops, excuse me. Right here. There we go. So there we are. We come back here now. You can see there's another little lake that's up in here, and it's draining down through here. This channel is now active. The ice sheet shrinks a little bit more, and it's off to the pond or this lake over on the left is still there, still draining down this channel into this lake. And this lake keeps on getting lower and lower and lower. And it's now leaking out this channel, and now it's leaking out this channel out over here. In the meanwhile, the ice is retreating up the Willoughby Valley, and the lake that's in this valley keeps on growing to the north here. So let's look at this other example, which is a little bit north of there. And this is the area I've been mapping in this year. So again, here's our, this is the boundary between the Clyde River Basin over here and the Barton River Basin. Essentially, this is the Route 5A corridor here, right there. And once again, a whole series of these old channels preserved up on the hillside. And there are quite a few of them. So just by way of geography here, this particular channel right in here is the one that Route 5A flows right along. So one of the problems I had in trying to interpret the geology of these channels was that if you think about or I was thinking about, well, what was the water source that eroded them? And if I kind of hypothesized a lake in the Clyde River Valley, it's much too low because the drainage divide over here in the Nalhegan Basin is really relatively low. So I started thinking, well, there must be another explanation. And so what I came up with was, what if that basin was filled with what geologists refer to as dead ice? And this happens a lot when glaciers retreat across the drainage divide. The ice gets very thin and it breaks off from the rest of the ice sheet. And you just have chunks of ice sitting there, like they're like great big ice cubes. They're no longer flowing in the way glaciers, most glaciers behave. And if you do that, then you have the Nalhegan Basin, filled with this stagnant, non-flowing ice. Then that gets dammed, and water from the melting ice sheet now ponds up and flows out here. And it's at just the right elevation to feed water into these channels. And this lake in the Clyde River Basin is at a much higher elevation than this lake here in the Willoughby Basin. So water's going to leak from here over to here. And so we'll focus in on this area, and I'll put together a series of sequential models of how this might form. So here's that lake, water dribbling out through this channel here. The ice retreats a little bit. Now it's draining out through that channel. The ice retreats a little bit more, and each time again, the lake in the Clyde River Valley is getting lower and lower, and water is flowing into the Willoughby Valley. So in this case here, of course, the water's now flowing down here. The ice sheet retreats a little bit more, and so now people driving along the road can actually, well, actually they can't drive because there's water flowing down there at this point. And a little bit lower now, and we get water flowing, again, still down this channel, but instead of using this outlet, it's using that outlet. And a little more, we start flowing here, and then through there, and through there. And again, all the while, this lake keeps on getting lower. This lake stays at the same elevation, and lower, until they finally merge together. And now, this lake in the Clyde River Valley and this lake here that occupies both where Lake Willoughby is and Crystal Lake are now all one lake. And they're draining out of an outlet over here. Now, if this ice sheet continues to retreat up to the north a little bit more, and so this outlet gets abandoned, there's a lower outlet opened up over here, and this lake shrinks. And each time this happens, of course, there's this big rush of water that comes out of these lakes into this lower level lake. In this case here, the big lower level lake is Glacier Lake Memphremagog over here. So at this point here, this Clyde River Lake gets sort of abandoned up here, and becomes a wee little thing. There's an interesting story here that a colleague of mine, Tim Cook at the University of Massachusetts, first brought to my attention, and probably a lot of you are much more aware of this than I was. But there's historical records of a lake existing in this valley, up until about until early settlement times here, just before European settlers started moving into this valley. And again, they describe it as having two outlets. So there's one outlet here, and this is the outlet up here just above West Charleston. And you can see they're both at the same elevation, almost. And the lake was described as being about 10 miles long, and that's what, if you dam up the water in there, that's about what you end up with. So I think this was a kind of one of those lakes that hung on for a while. And of course it says something then about this funny geography of the Clyde River in this area, where it just meandered back and forth through this really, really wide, extensive floodplain. And there's very little sand in this area here. It's a bottom up. And probably all that lake bottom up that it collected for the better part of 15,000 years. So if we go back out now to the main basin, if you're, I'm sorry for getting tired of looking at these things here, but I'll just take one more of these steps here. Here's the lake in the upper Missisquoi Valley, and here's the lake in the Black and the Barton River valleys now merged together into one lake. And I'll draw a little topographic profile along that red line, so we can see that this lake up here is quite a bit higher in elevation than the lake down in here. And of course, what that translates to is that at some point when the ice sheet retreats to the north, there's going to be an escape route because this ridge up here gets lower and lower and lower as you go to the north. And sure enough, these are the channels that routed water, I think, from the lake to the left in the Missisquoi to the lake on the right in the Black and Barton River valleys here. I'll also point out, you can see this channel here, you can see this channel here, but right in there, there's no edge to the channel. And this is another way that we can infer that if these were connected, the only way they could have been connected is if there was something to hold the water in. And that something was the ice sheet. The glacier was there. So I'll show you a view of this where that arrow is right there along where the Collins Mill Road. This, by the way, is right near the intersection of Route 100 and Route 14. And then we'll look at a map right in there. So this is what a lot of these drainage channels look like. Again, they tend to be these low areas, a lot of boggy vegetation in there. I was telling John and Ben on the way up, they're good at the ski nurseries. A lot of kind of standing water in there. So here's the detail here, and when we look closely, you can actually see that with this one channel. Look at all those little distributary channels right in there. Essentially you can see that on this little area right along the side of Route 14. And this is all sand and gravel up in here. So I think these are all deltas, essentially where the lake in the Missisquoi Valley is draining out, produce these little deltas, in the lake that was in the Black River Valley. All right, so there we are. So first utilization of the first channel, the upper channel, then the lower channel. And once that pulls back, then those two lakes, essentially merged into one. And eventually we have, just one big bloody lake. And this is Glacial Lake Memphremagog. And Glacial Lake Memphremagog is still draining out of this outlet along Route 14. Headwaters of the Black River, which is what Lake Elliott is right now. And again, at this point here, Crystal Lake, Lake Willoughby are all free of water. Most of the Clyde Valley, is high and dry now. So as the ice sheet continued to retreat north, the lake continued to grow. And so now we're looking, at, here's the margin of the ice sheet up here, and I've drawn this based on some good work that was done in Quebec a number of years ago. And so this is just actually the partial extent of the lake in Quebec. It's quite a bit bigger than that. So big lakes. Big lakes, small lakes in a lot of these different valleys. Well, what's the consequence of that? Well, a consequence of that is that these lakes are full of sediment. Right now, if you go out in the modern lake, for the most part, it's clear water. Glacial lakes, though, are not like that. They're muddy. They're full of sediment. And this is because the glacier is constantly kind of feeding sediment into the lake. And that a lot of the coarse stuff gets settles to the bottom relatively close to the glacier, but the whole of the lake can be muddy looking. And that mud, silt and clay-sized sediment will eventually kind of settle down to the bottom of the lake. And this is what it looks like. You see these layers of silt and clay. Sometimes they're layers of fine sand. And in the geologic map here, this is just a portion of the map that's spread out on the table. So we're physically sitting just right about over here right now. But all of the blue here are these fine-grained glacial lake sediments, all of them deposited in glacial lake Memphremagog. When you get closer to where the shoreline is, or where streams and rivers come into the lake, then the sediments get coarser. I'll say a little bit more about those in a bit. So here's another example. South of us here, down in South Bay. This is the railroad grade coming down through here. Of course, all of these wetland sediments out in the bay, south of the open water. And here's a cross section of the prison, by the way, it's right here. I do this cross section based on a couple of water wells, and you can see there's a considerable thickness of these fine-grained glacial lake sediments. And then they come down, and then there's a layer of that till, the peanut butter, the crunchy peanut butter, and then you get down to the underlying bedrock here. So something else that is happening in this area, all ice sheets, or all glaciers, the water that melts on them, sometimes stays at the surface for a little while, but most of the time it actually finds failures and it gets down to the bottom of the ice sheet and flows along tunnels. So this is an example of water coming out of a subglacial tunnel on a valley glacier up in Alaska. And sediments that get deposited in those tunnels are essentially stream sediments. It's just that they're deposited in a tunnel instead of a stream valley. And when the ice melts away, those stream sediments are left sort of as an inverse stream valley, and it forms a ridge. And so just up on the Quebec border here, here's the Missisquoi Wildlife Refuge up in here. This brown is one of these ridges that's referred to as an esker. Mostly sand and gravel. And there are also a lot of these little wetland areas in here. And these are some more pieces of the ice sheet that broke off and essentially form these little depressions, pebbles. So this is a little model. One of my mentors, Fred Larson, who taught at Norwich University, put together, showing a retreating ice sheet and one of these eskers down in here. And the other thing that's happening, of course, is that a lot of the sediment is kind of spewing out of the glacier, sort of like a big fire hose of sediment. And so here's another esker over here in the Stony Brook Valley. Again, think the Route 14 Valley here. That's what that dark brown ridge is. All of that lighter brown sediment around there is stuff that looks like this. And this again is another photograph of Peter Strand from another geologist at the Vermont Survey. And this is some of that finer grained sediment kind of deposited in the lake that's sourced directly from this esker tunnel. So here's there's a great big pit, up here on the east side of the lake, and it turns out that that sand and gravel that they're pulling out of there was actually deposited in the delta. And this was a delta that was produced, I'm pretty sure, by the Clyde River flowing into glacial Lake Memphremagog. So some of this, there's actually an old town pit just up here in the city. It's sort of buried in the woods up there, but that same sand and gravel is right up in there. So, and this is what that material looks like. And some of the sediments are structured in a way that's very, very distinctive of those that are found in the delta. So I wanted to put together a little story here then. So here's glacial Lake Memphremagog, and here's the delta that we see on the east side of the lake, what I think are some of the same sediments on the west side of the lake. And I asked myself, well, what if those were once connected? And one of the reasons I think that is I can't see another source for the sand and gravel over here, except the Clyde River flowing into the lake. So if that's the case, and if I'm correct about this, then that leads to a sequence of events that might have happened. It might explain, sort of the segregation or separation of the South Bay, from the main lake here. So first of all, we'll think there's the delta, and deposited in glacial Lake Memphremagog. And what if this, again, at some point, glacial Lake Memphremagog drops in elevation by a lot. And this happens when the ice retreats north and west far enough in Quebec that it uncovers a lower outlet. And it drops about 85 meters, which is several hundred feet. So boom, the water, would be like you're out here in the lake and you look out there and you think, geez, the water's falling, so the water to the north will be free to fall, but essentially this delta here then I think probably dammed for at least a short while the water to the south, where South Bay Valley is. In other words, it just didn't drain as quickly. So then what if that water that was pooled up in here started working its way across that sand and gravel delta? And it's just sand and gravel, it's pretty easily eroded. And again, this water then kind of eroded out this channel here, making the narrow channel that exists just to our south here. And essentially, eventually everything stabilizes at this lower elevation. And that lower elevation, it turns out, is the elevation of this terrace up here that much of the north part of Newport is built on. Maybe some of you live on it. Up there. It's all underlain by sand and gravel except for this bump up here. And so, and I think it was all essentially deposited by the Clyde River, after the lake level fell. So here's this lower level lake then, and it's extending, up into this part of the Quebec here, and it actually, this Lac Nick outlet is here, and it's going eventually out into the Francisco River Valley, blah, 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 blah. And you can see this is actually this part of this bigger map here. So even at this relatively low elevation, this lake covers a huge part of southern Quebec. So I'm gonna finish up there. This is, I think that's my last slide. Yeah, I think so. So, but that's the end of my lake story. So thank you very much. So I would certainly, and I think John as well, be happy to entertain any questions either now in front of the group or informally afterwards. That's the general.
We can do 5 minutes now and then run through our brief slides and then your Sopa season.
Sure.
I'll start it off. I got a question.
Sure.
So I'm familiar with glacial Lake Missoula floods and there's lots of landscape features and indicators. Are there things that lake people can see in the landscape, like lake level striations anywhere? I mean, our tree cover probably prohibits that, but any other obvious indicators that people can see driving down the road?
You mean for these lake level?
Yeah, fluctuations.
Well, the channels, and I've showed you several examples of some of these channels, but they're just all over the place, and it's one of the things that makes mapping in this drainage basin to me a little different than the other areas that I've mapped. And occasionally you'll find a channel here or there, but here you find these nested channels all over the place, and that's so instead of having I think in most cases the ice sheet retreated and a channel formed. The ice sheet retreated a little more and a channel formed. And in fact, that, you know, there's part of me that wants to think that they might even be yearly, you know, on channels, you know, marking sort of the shrinking of the glacier. But, yes?
Yeah, I'm curious about the time frame during which the glacier receded just the distance of, for instance, Lake Willoughby, to be able to create each independent kind of tributary channel there. How long was it moving just the distance of that lake?
At the time frame that the ice was retreating, you know, across, again, much of this area of northern Vermont, one, we don't have any direct record. Two, a little farther south, though, you know, south and east in the Connecticut River Valley, we know that the ice sheet was retreating. In other words, the margin of the ice sheet year by year was retreating up to 300 meters. So think almost 1,000 feet. You know, so you set up your tent at the edge of the ice sheet one year, and the next year it's 1,000 feet away, and the next year it's 2,000 feet. You know, so 5 years and it's retreated almost a mile. You know, but the other thing with these channels, of course, is that sometimes you're thinking about where the margin of the ice sheet is, but you're also thinking about by what amount is the ice sheet thinning, you know, and which is a smaller number. But to lose that much ice every year, you know, you're actually thinning the ice quite a bit. And it turns out with a lot of these channels, you could think that, you know, the distance and elevation between them ranges anywhere from the elevation difference between the ceiling here and the floor to maybe twice that. And that's you know, if the ice sheet is retreating at 300 meters a year, that's a very realistic thinning. So that's one of the reasons why I think, I can't prove, but I sort of like the idea of these things happening on a yearly basis. Yes?
I was, as a layperson, I always been taught that glaciers carve things out. It seems like it's less carving and more filling of sediment into these big holes where the lakes were.
So I missed the first part. You said
I've always been taught that glaciers carve things out.
Oh, they do.
It seems less carving and more of sediment filling. Is that incorrect?
No, both things happen. Glaciers tend to accentuate the pre-existing landscape. You know, so I think when you think of the major valleys here, they probably were here before before the Pleistocene Ice Age. You know, so before 3 million years ago. So one thing to think about, you know, in a valley like, particularly the Willoughby Valley, that's so striking and, you know, looks so much like a glacially carved valley, and it was. But during the last 3 million years, you know, we tend to think about this last glacial period, which lasted, you know, roughly from, you know, 120,000 years ago to 13, 14,000 years ago. But there have been roughly on 100,000 year timescales other glaciers that have come down. So it's not just one glacial episode, but probably a dozen, 2 dozen, maybe more. You know, how many of those ice sheets that formed became large enough to decide that they wanted to cross the Quebec border into Vermont? I don't know. But the point is that you're absolutely right. You know, there's been a lot of bedrock erosion, but it hasn't been the glaciers weren't the thing that actually made the valleys. A lot of those are based on weaknesses in the bedrock that essentially lead to the rock eroding faster in one place than another. And that's happened over time spans of tens, if not hundreds of millions of years.
And as the Laurentine melted, would it be true that the southernmost would have the most sediment because it's more and more of the stuff floating around it, or is it?
No, it's just probably it's more a function of the rate at which it's melting, and to a certain extent the underlying bedrock, how erodible it is. So that glacial till that I showed you a picture of, that's the source of a lot of the sediment that ends up being deposited in these lakes. In other words, if you take glacial, till and erode it by running water, the streams that are flowing underneath the glacier, there's going to be a lot of mud in it, and that's going to end up being distributed, and that's all the blue sediments on my map there. The sand and gravel that was in that till, that's the stuff that's in the delta. So, John, yeah.
I just want to bring something up about this whole thing about the glaciers accentuating topography. There's one thing, if you've been to Lake Willoughby, and then you go over to Crystal Lake, you go, they are exactly parallel. So why was that? Is that just the glaciers, and it's not? There are very conspicuous fracture zones around Lake Willoughby where you actually, there's a probably Cretaceous fault zone, not active of course, that defines that direction exactly.
As well as tectonic plates moving too, as well as the plates moving too, or is it just a fraction?
Sorry, you said that again?
As well as the tectonic plates moving too, or just fractions?
Well, so in terms of the whole history of, say, North America, that was probably around 100 million years ago. And so the Atlantic had already started open, maybe around 200 million years ago. But you have these extensional events across this point part, or where the crust is sliding past. And so we have, if you go to the south end of Lake Willoughby, I can show you, we have a field trip. And you'll actually see that there are zones of very closely spaced cracks. Parallels this fault zone defines that direction of Lake Willoughby. When you kayak around Lake Crystal Lake, on that far, that big wall on the east side, you see the same things. And it's cracks. So the glaciers were utilizing pre-existing zone of weakness. And that happens a lot. And that fault that I was talking about, one that is essentially runs on the southwest side of town, and that connects with the La Guadalupe. Faults can be very zones of weakness for erosion. And one of the reasons you see that pronounced ridge, say you're coming out of Casella and getting on, I forget what road that is, and then you see this, Patrick, what's the name of that ridge?
Airport.
No, what road is Kyle and Sarah live on?
Import Road. Anyway, that pronounced ridge that you can see, we can look on Stephen's map.
Parallel Coventry Road.
That ridge is there because the older rocks on the top of that are harder to erode than the ones down lower on the east. And so that's why that ridge is there, but I can show you on maps that we can track that ridge all the way into southern and back way north, and I can track it. We could start here, drive down, have lunch in Craftsbury, it's there, drive Montpelier, it's there, we'll take it on to southern Vermont, it's there, drive you down to Greenfield, Mass, it's there. And anyway, so that's an example of erosion resistance providing essentially the quote force that allows that to stand high.
A question about how you actually coordinate study between the two countries. So I take it you never did see the deep throw, that you never saw an actual line that divides the U.S. and Canada. Physically, it's not there, is that right? But that's my joke. But, as a dual citizen, I'm quite interested in the comment about the border and how the two countries, like how do you actually coordinate study between geography that's in the United States that continues on into Canada and vice versa?
Okay, so I can speak for myself. So since 2000, I've been going on field trips with Quebec geologists from Quebec City, Montreal, on field trips where we spent a whole week, where half the week we're looking at southern Quebec geology, and then we're looking at Vermont geology. And we've been talking, comparing over the decades. And it's a wonderful collegial profession. And we love our Quebec colleagues. And we've written journal articles together. And then when we take this information, though, so it's not just in this, say, academic vacuum, but we're able to compare issues, environmental issues, or the background behind certain environmental issues that happen in the States versus in Southern California.
So I'll say for the glacial geology too, the same thing. We go on each other's field trips as best we can and try to learn what we're doing. But physically on the map, you see, I've mapped stuff up to the border and boom, stopped. And there's no reason why I can't go across the border and map there. But the truth of the matter is that most of us are stressed enough for time to map these areas as it is. So as soon as you see the border of your map, you think, yes, I'm not going across there. Well, not really, but it's a practical thing as much as anything else. And I think the map that John showed you of the geology, essentially of that whole part of the Appalachians that extended, across New England and into Quebec. Those are people who sat down and pulled maps from, New England, pulled maps from Quebec and so on and so forth, and merged them together after, lots of collaboration and field trips and so on and so forth, and back and forth.
I wanted to add to that too, from the overall watershed perspective, there's something called the Quebec Fund Steering Committee, and it's both countries meet twice a year. One of the meetings this year, and one of them is up in Canada, in Georgia, and there's a lot of collaboration back and forth, and share data with each other, and trying to forward on
And another piece I'll add is that there just aren't that many of us doing this.
All right, so bear with us for 10 minutes. We'll have you out of here, or you can linger and pester John and Stephen as much as you want.
So we're going to talk right now?
Really briefly, and then we can open it up to just a mingle. So, as mentioned, I'm Patrick Curley. I'm the project manager for MWA. We're just trying to run you guys through what we've been up to this year, heading into next, in terms of our grant projects and our work to actually to restore this watershed of ours where needed, protect where we have great conditions. One thing that was extremely humbling about this talk that we just sat through is that restore to what? Restore to what conditions? Restore glacial Lake Memphremagog. Like, let's get a hurrah for that, right? Let's plug that ice sheet again. So these are some of the projects that we're working on. I'm not going to go through these. I just want you to know that we're really busy. We've got, as Tom said, since 2021, we've pulled in almost $3 million in grants. That almost all of it goes back into this community, back into this watershed, to businesses that help us implement the work, firms that help us design or acquire property and conserve them, and then lands that we actually rehabilitate. And we're going to show you a few examples of what that looks like. We get funding from all sorts of places, primarily the Great Lakes Fisheries Commission, which is a binational effort to manage international water bodies like Memphremagog. We get money from the Vermont Housing Conservation Board as our clean water service provider, Vermont Fish and Wildlife Department, a whole slew of others. One of our projects is right up on Hinman Settler Road. This is an alluvial fan restoration. So this is a stream that was historically ditched, straightened, dredged, channelized, everything you can think of. And we essentially created a new channel, turned the water out onto an existing wetland meadow, and we are letting that sediment and water spread out, deposit as it willingly chooses. And then the stream actually finds its way back to a forested brook where there's tons of brook trout. So we're trying to restore the kind of depositional features where we have those glacial till deposits or silty deposits. That's where that phosphorus can actually get trapped in the landscape. We're in a bit of a drought, so not much water flowing through this brook right now. Another one we've been working on, you probably heard before, on Valley Road in Morgan. This area was, again, a bunch of other alluvial fans where we decided to put a tiny pipe and a big road across a huge delta-type landform, and streams don't like to behave that way. So we are taking things like an 18-inch pipe in that disastrous deposit of silt you see right there and turning into an 8-foot by 5-foot box culvert, and then blowing out a half-acre landing zone for all that material to come down and deposit on property that we acquired and conserved with Fish and Wildlife Department a couple years ago. This is all 150 acres of public land that you can come fish, hunt, look at critters. So we're working on 2 culverts this summer, 2 culverts next summer. We're planting almost 12 acres of trees, and we're reconnecting 1.5 miles of perennial stream for brook trout. Another project, a little different flavors in Barton. Ed Barber, if he's still here, he's heard me gripe about this project for 5 years, trying to get it over the finish line. But this is down the community garden. We're taking a knotweed infested patch and we're diverting stormwater from the existing 6.5 acre downtown municipal drainage through a series of treatment practices that then disperse, infiltrate into the ground. Great sandy loam on this site, boys. So the water's going right into the ground primarily. And we're also working really close to the community garden, Solid Rock Assembly of God Church, the village, V-Trans, the school, far too many players to name. But this you hopefully will see in the construction in either October, November, or April. Just up the road in Glover, we're trying to implement another stormwater management project. This is very small scale, more of a touchy-feely, experiential, very public-facing, visible project. These are rain gardens. They manage the runoff from the rooftops, the Bean Hill Road, the parking lot of the fire department, the town office, and we're essentially making these infiltration practices with folks like Northwoods and Greenleaf Design, where we can show people what responsible stormwater management looks like when they go to drop off their biannual taxes. So you can see this project is kicking off on August 25th. Feel free to swing by the Glover Library and take a peek. We do weird things with wood. This is right near the I-91 interchange in St. Johnsbury, where 2 crosses. A whole kind of chaotic interchange system, and with all these floods, we had a lot of debris come down and plug these huge culverts underneath the highway. V-Trans went in and pulled them out, but then all this giant wood was sitting on the banks. And so we got a grant to then hire a logger to go to and pull the wood out, drive it up to the interstate shoulder, load onto trucks, bring it up to Derby and Newport, and we're using these logs for restoration projects. So these are 40-foot logs with big 6-foot root wad fans on them. That's very valuable timber for us because it helps we use it to help stabilize stream banks, create fish habitat, reduce flood intensity, protect infrastructure. We use them as integral pieces of a restoration project. We spent $20,000 retrieving 3 log truckloads full of wood. That would have cost $75,000 to procure if we had just hired somebody to go out and dig these out of the forest, which we don't really condone. So we help the V-Trans system, help public safety, get cheap materials that are great for our projects. We're going to use these logs, for instance, on this project. This is a farm that we conserved last year with the Fish and Wildlife Department. 26 acres here, plus another 2.5 that we're going to get from Stansted, Canada, who owns another lot right next door. They're going to donate it to us. It's going to be part of this fishing access area. It's going to be about 30 acres in total. But you can see there's a couple agricultural ditches. This is a relic channel. This is a ditch and straightened, artificially straightened channel. We're going to do a lot of work down here, plant about 10 acres of trees. There are 2,000 fish per mile in this section of the Johns River. You can almost see the esker that Stephen pointed out. In fact, on my home screen, you can see it. We do a lot of weird things, as I mentioned. In South Albany, there's a ton of tiny little pipes with big beaver complexes just upstream. And so this is our 3rd beaver deceiver, or a culvert protection structure that we put on the inlet of pipes on rural roads where we're not going to be able to spend $100,000 to put in a bridge, right? So this is a adaptive management project where there's so much perimeter and leakiness to this cage that the beavers can't plug the culvert. So this is a flood resiliency project. This is a beaver coexistence project. We don't want just the old 22-round solution. We'd like to let the beavers do their thing, but also have our roads not wash away. So this is the 3rd one we built with Northwoods out in Albany. They've been great to work with. We also do strategic planning for different watershed or different lake watersheds. So we've completed the Willoughby one. Man, I really wish, Stephen, I had known about those little steep tributaries when I was doing this work, because I would have stopped scratching my head about why there are so many that are dry. So that was pretty mind-boggling. So thank you for that. We've done one for Echo and Seymour. We finished that last year. We're about halfway through the Averill Lakes Lake Watershed Action Plan. This is a tool that brings together stakeholders, brings together the professionals, the working lands, the lakeshore owners, and science and field assessments to figure out where is there concerns for water quality and fish, what can we do about it, and then trying to develop and design projects that will remedy those issues. So we're working on A-rolls. These 3 are already complete. Will Marlier here from Orleans County Conservation District is our lakeshore coordinator now. He's new this spring, and it's his duty to pick up this work and keep running with it. So we're happy to work with Will on those going forward. Gabby's going to tell you about some projects more close to home. Just so you know, we like to look upriver to solve some of our problems. We can't just fix it once it's down the lake. So that's why we work on a lot of these headwater tributaries. But Gabby's been leading the charge on a couple right along the shore, which you can see out the window.
We're carrying some lovely silt fence, having a ball. This is a really awesome lakeshore workshop we were able to do. Just following our Lake Watershed Action Plan in Echo and Seymour watersheds, we were able to get a really bad ditch disconnected from the lower portion of the ditch where a stream comes in, and get that back onto the landscape into this beautiful wetland. And the landowners were also really agreeable to fencing out the wetland area from the cattle. You can see this is where the culvert cross drain comes out. We have a stabilized outlet to reduce erosion, and this is actually like a little cattle crossing. So you know they can have some access to water and then walk around as well. You can see everyone's in their snow gear because it was snowing the whole day. It was great in the spring, and then we're getting a planting going along the shore, or along the Cranberry Brook with willow stakes that would grow into willows, and then we also planted a bunch of shrubs and trees along the shore as well. So, and that was with the Conservation District and Northwood Stewardship Center. We had a great turnout and got a lot of great stuff done. This is our Scotts Cove Lakeshore Enhancement Project. We've been working on this since last year. We have Abraham Ames, our invasive species specialist, getting out and working on 2.5 acres of removal for Phragmites, reed grass, and he's also going to be expanding that into the Bluffside property and all the way into the cove, expanding from 2.5 acres to 5 acres, and we're now treating yellow flag iris and purple loosestrife as well. And then after all of that, we are coming back in with Northwood Stewardship Center crew and planting 10,000 wetland plugs of bulrush species. So we're just about, we only have 1,600 plants left, getting those in next Monday. Help yourself to go and to check out the boardwalk at Bluffside. You can actually see the lake before it's just crowded out with Phragmites. You can see down, if you look down, it's like really thatchy brown areas. That's where all the Phragmites were, and now you can see a lot of great bulrush and native plants coming back in because we cleared that space. So really awesome project. Yeah, so help yourself and enjoy it.
Gabby, are you going to do it all the way down to the tip end where Bluff Road is?
Yeah, we're working our way to your house. I've got to talk to you about that. I see you have a little bit on your property too. All right. And then here's another project that's been kind of kicking our butt these last few years, but we're getting there. We're about to get permits going. This is a project in Newport off of Velco property. It empties directly into the Clyde and then right into Lake Memphremagog, so really close to home. There's 2 major sediment sources, one that's a forest gully and another quack, quack, and another that is from a bass trail. And we wanted to stabilize both of those sediment sources, leave the sediment up on the mountain before it comes back down and enters into the lake. And then on the way down, we're seeding, we're putting in woody structures like Patrick was saying. We're building beaver dam analogs, which are basically beaver mimicry structures. We're building little dams, weaving them in, putting down strategic wood additions to slow the water, get water out of the channel, depositing sediments on the floodplain, leaving them as they are, and really improving habitat for fish and for other wildlife in the area. So that's going to be a really awesome project. You see, this is one of the sediment plumes that we're trying to stop in its tracks and stay there. And here's the channel. You can see how unsized it is. We'd like to put some structures in here, raise that water table, and have it stop scouring down into the landscape and just pushing those sediments through. So we'd like to, really improve this habitat and this stream function. And that's a little picture right there of what Beaver Dam analog looks like. Just weaving. And then here's Ben, our new project coordinator.
Hello everybody, I'm the newbie to NWA. I've been in this area though for quite a while. I moved here about 25 years ago and I love it here. I have been tasked with kind of doing a scoping effort for the Clyde River to see if it might be designated for wild and scenic river designation. This is a national program that was started in response to all dam building in the United States, particularly in the 50s after World War II. In New England, obviously there's not a lot of public land, so there's a unique type of partnership, wild and scenic river, called partnership. And what's really cool about that is that it's a partnership between the National Park Service and local communities. So in addition to going around and checking out all the cool things about the Clyde, remarkable features of the Clyde, I'm also going to be reaching out to the community, people that are passionate about the Clyde, people I would call river stakeholders, but also just people that like to enjoy the Clyde. And so I'm about to launch an effort of interviews and surveys of community members. And this is a long-term effort. It's usually about a 3-year process once you get an official study. So we're just trying to get a sense of if there are enough community support to pursue this. There's kind of 2 big outcomes. One, you energize community about a particular river, and in this case the Clyde, which is quite a remarkable river, I think, as Stephen kind of alluded to earlier in his talk. But the other thing is it's another pot of money to tap. It's federal dollars that's in the National Park Service budget. So assuming that we still have a National Park Service, I'm going to hold my fingers there, in 3 or 4 years, we could have another source of money to do restoration projects, but also have river access and get people on the river. The more you get people on, out into the nature, on our rivers and lakes, the more people care, the more we can do. So I think I just have one slide, right? Yeah. Oh yes.
Oh yes.
This will be released soon. I'm actually going through an institutional review board process at UVM because the other thing is I'm a master's student in the field naturalist program at UVM, and so this project is in partnership with Memphremagog and my program. And so this will be a flyer that will be popping up in country stores and libraries and public spaces all over the Clyde River community, so to speak. And I'd just like to say a real thank you to Patrick and Gabby and all of the Memphremagog Watershed board and team. It's been a wonderful summer to work with them, and I look forward to maybe moving into MWA. So that's really awesome.
All right.
We have 3 plugs. One, if you love picking trash and tires out of the river, join us. You see the information. The second one, these 2 guys need rocks. So if you have a well, or you know there's bedrock on your property, and you don't mind some guys with a hammer coming by and clinking at it, contact John or Steven, because the more dots on this map that they can get, the better their data, the better we know about our watershed, and there's only so much public land. So if you are willing to have a geologist come over and look at your stuff, you know how to get in touch with us, we can get you in touch with them. That would be great. So think about it. The third plug I kind of forget. No. What's the third plug? Oh, board members. Yeah. If you're looking to join this fabulous organization and you have energy and you have interest and passion, reach out. We'd love to talk to you. Yeah, we're here for you.
Our next board meeting is September 10th at 5 o'clock at the Work Commons, which is the Montgomery Ward Building in Newport. And you're welcome to attend. And the other thing I'd just like to say about everything you guys are doing is it's taking out a lot of sediment and phosphorus out of the lake, which is helping to really improve the quality of our lake, decrease the cyanobacteria blooms, and bring it back to the way it used to be a long time ago. So thank you all.
Sure. Thanks, Tom. And if you are a river champion and you want to learn more about wild and scenic, Father Ben. He's here for you.
Surveys, do them.
Yeah, do the survey. So thanks everybody. There's some more peck-ins to have if you want. There's still questions that can be asked. You can stay as long as you want. Tip your bartenders and have a great night. Thanks for coming out.